My name is Jason, and I'm a pure mathematician and turned AI researcher recently. During my postdoc and PhD, I was using Fourier transform to study some real-world phenomena such as wave and quantum mechanics, and basically describing them, the behaviors, and the approach is using Fourier transforms. So it's a very theoretical field. So this is a big change to move on more applications and actually code things. I've never coded until before September last year, I think so. Anyway, so the flow of this discussion would be very hopefully trying to be intuitive in the meaning of Fourier transform. So here, if we have two photos, we have the lemon cake on one side and the ingredients. So if I tell you, like, one can actually do something on the cake and then produce the exact amount of ingredients for every ingredient. So that sounds impossible, right? And well, we can do it by eating the cake of it, and then we can say what is in there. But we cannot actually say exactly how much of each of these ingredients are there, right? So for what the Fourier transform does is actually give exact, if you have a cake, it will give you somehow the exact ingredients of that cake. Every ingredient existing and every amount. So to see that mathematically, next slide probably. So that idea also is quite huge, because actually Joseph Fourier formulated that while he is studying the nature of heat. There's a long story for that, but let's keep it that way. So let's look at this photo on the left-hand side. So if we have a signal, which is the red one, so what the Fourier transform claims, is that it gives you the ingredient signals. The ingredient signals are basic signals, meaning they are the same, oscillating at the same time for infinite amount of time. So this says, it seems like for this particular signal here, we have three ingredients, we have three frequencies, and you can see on the Fourier domain that only those frequencies would have values, and the other ones are almost zero. So that is the basic idea of Fourier transform, and decomposing waves into basic sine waves. So this is applied in physics, in partial differential equations, which is where I mainly work, and quantum mechanics, MRI, signal processing, any time series, definitely. And if you can reformulate your problem, virtually anything, you can use this idea. So now we be careful in what we are saying. So we have some definitions. So I will denote here the operator curly f as the Fourier transform, which maps something from a complex domain to a complex domain. That is important. So seeing this formula here seems quite intimidating, but what it does is exactly what we want to do. What my claim earlier is that we can separate frequency, right? For that to make sense, we should have some machinery to be able to separate things, right? In this case, the machinery is this exponential function, e to the minus 2 pi I omega t. So what is this? This is a complex number, and if you change t, it rotates, right? It rotates on circles. So that's kind of your unwinder, and your f could be a real function or a real valued function or complex, in general, complex valued function, because real is a subset of complex numbers. So you take the product of those complex, and then you take the integral, infinite integral, and you get the definition of a Fourier transform. So what are the ingredients here that I was talking earlier? So here, if you ask, like, does it have frequency 5, for example? So you plug in here 5, and then just compute this. And then it will tell you if it's a big number or a small number. If it's a small number, probably it's not really existing in your function. If it's a big number, then you're sure it's quite there. Okay, so I hope now this mathematical equation makes sense, that it's a machinery to unwind frequencies by getting all the basic frequencies, but asking here, you put here what you want in this omega. Now the discrete Fourier transform, which is what we want if we want to use computers, because computers understand discrete things, unfortunately this there's a long way from here to here. This is not something that you would simply take finite points here, because this is an infinite integral. So the discrete Fourier transform, 1D, maps a complex number n to a complex number n. This will be clearer later. And notation, say you have you want to know now your discrete sample f would have a frequency k, then there's a formula which kind of looks like this, but different in meaning. There's also this inverse in which you want to get back, you want to remake your, because the capital FK here are your ingredients, and so you want to remake your original sample signal from that. Now to make this clear, this path from discrete to let's talk first about some properties. I did not put all the properties, but the ones that you will see within this discussion, which is linearity. So to think about this, if you have a cake and a lemon cake and a chocolate cake, if you want to know the ingredients by taking the Fourier transform, then what linearity says is just know the ingredients of individual ones. And shifts, meaning you're shifting, you're moving in space or you're moving in frequency. What we have here is formally, we will say you are modulating your function f by this oscillation here, and then you're taking the Fourier transform. So what this shift says, that vibrating in space is just moving or walking in frequency, and vice versa. If you walk in space, translation in space or time, then you are vibrating in frequency. And convolutions. So the identity here tells us that if you take the convolution of a function f with some kernel, n here stands for that the length of this discrete thing is length n. So convolution is just multiplication of the Fourier transform of f and the Fourier transform of the kernel. Now I want to take this opportunity to clarify things which I usually see in deep learning. So this is, say, this is an image, f. This is your kernel, k. And this is the Fourier transform of the image, capital F. And this is the filter. This is actually the filter. But a lot of times I think people can use this use this what's the term, interchangeably. And the thing is, what does a filter does? The word filter means that it lets something pass, but because of some rule, right? So what you're filtering are actually frequencies. So, but it's not so bad that filter and kernel are used interchangeably, because in a sense, if you choose a kernel, you are choosing your kind of filter. So, okay, so how do we go from a mathematical idea of continuous functions to use it in computer, which gets discrete samples? So this is thin Gaussian, continuous function, infinite length. Actually, the Fourier transform for Gaussian, so this is the only reason this two looks the same, because that's a special property of Gaussian. And so you can get this by direct calculation. Now, if you play around this function and you have, say, a periodic extension of this function, sorry, the blue one, you repeat it infinitely many times, that is the only time that you will get discrete numbers. So that realization here enabled us to actually use Fourier transform to computers, because now you want to move reverse, because what we get are discretized signals, right? So you get the discretized signal. But if you just take the Fourier transform of this, it's still an infinite and continuous way, which is called the discrete time Fourier transform. Discrete time because you have sampled. Your time is discrete. But if we now if we sample this, you can get the sampled version of this. What is actually happening when somebody talks about taking a discrete Fourier transform of something in computers is that we are moving from discretized function to this discrete, this picture to here directly. So that is, but that is okay, because there is an algorithm now. There are algorithms, and one is called fast Fourier transform that helps you move from here to here. But take note, fast Fourier transform gives you one cycle of this, but actually there are infinitely many of these signals. But what it actually gives you is just one cycle, which is enough for us to do a lot of things, actually. And this is just to show you what it looks like to extend the definition of a 1D Fourier transform to 2D. And what is this? The idea is simple. You do it by variable. You do the 1D by variable. That's it. So say you have this red thing here as our photo. And so if you want to take the 2D Fourier transform, you take the 1D Fourier transform per row, and then take the 1D Fourier transform again per column of the resulting thing. So this is it, right? And this is the recovery. Notice it doesn't need to be a square image, as would be in my example later. And okay, so say this is a photo, 6 by 6 pixels. And that's why I said pixel intensity space, or you are in the spatial domain. And what the discrete Fourier transform, or safe to say FFT, if you do FFT here, because this is the algorithm that does compute the discrete Fourier transform. Do the DFT, what it gives us is the same size. Should be very same size, right? And complex valued. Okay, just to remind us that we mentioned that earlier. You can see here, complex valued to complex valued. I think from here I want to show some photos, because okay, so what are complex numbers? What information do we get from each of these entries? We got magnitude, which is like their weights. You can think about that. Oh, and frequency. So for reconstruction of this, we are using these guys, right? And sorry, gosh, so I need to run this. Okay, so what I will try to show you is that if you have an image of Fourier transform, so each of those complex numbers earlier in those entries would be some simple photos of stripe patterns, horizontal, vertical, diagonal. It depends on where they are. And so combining the number of those plus some weight on how much weight do they give would recover the photos. And you will see later that you only need very few of these to recognize a photo. What? Run? Why did it say 30 here? Sorry. Okay, never mind the numbers. So I defined something.
Sure, just to check, are you showing something except the slides? Because I'm not sure if we are seeing that.
Oh yes, I am. Sorry, it's not shown.
I can't really. I don't think so. So maybe
I don't think so too. Yeah.
Modify the screen sharing to share the desktop and not just the application.
Ah, I see. Okay, thank you. Okay, wait. Now is it fine?
Yes.
Yeah? Ah, sorry. I see. Thank you. So here we're just defining vertical stripes and horizontal stripes using sine. And what I want you to understand in this photo is that your pictures are 2D functions of two variables which you graph in a 3D space. So this is some stripes graph in a 3D space. So what we're doing earlier, taking the Fourier transform of a 2D function makes sense. And here, I named it F10 to mean, what I mean is frequency that changes in the X and doesn't change on the Y. So what it gives us is here, right? What I mean by changes in X is that if you move from left to right, if you move your finger left to right, you feel there's a change. If you move it up and down, there's no change. So F01 would be this photo, and combination would be some grid, which in 3D would look like this. Now I also defined functions to give us what are the existing frequencies. Since these are pure sine functions, what these pictures earlier, like F01, so my function Fourier view only gave us this two. Actually, you can think of just one. On this photo, the frequency 0, 0 is in the center. So if we go back here, what I mean by frequency 0, 0 is this. So So the important thing of looking in the Fourier transform side is it gives you a geometric interpretation, geometric property of your photo. So you see these two frequencies that are active are on the vertical line. Yes, vertical line. And so that means there's change when you move up and down. So that's why these are horizontal stripes. This is from the horizontal stripes function. Now if I change this to 1, 0, you get vertical, the change in frequency that lights up. And the sum, which is this grid here, would be lighting all of the frequencies there. Now that is for a simple simple photograph, right? This is my profile photo I use. This photo seen in 3D in what I call intensity plot would be a mixture of several frequencies. So you can see the oscillations there. If you simply take a Fourier view, then we don't get much. And the reason for that is the range of the values of those complex numbers earlier would be, the range would be so huge such that it cannot be fixed in a 0 to 255 scale. You cannot see them properly there. So if you do a log, then you can see better, but with added noise. By the way, Emil, how is time? Hello.
Yeah, sure. Go ahead, and then we can jump into discussion when you're ready.
Okay. Okay. Yeah, I think I'm. So, okay. So this is a reconstruction. As I've mentioned earlier, you want your Fourier transform which moves something from a complex number to a complex number, right? So that's why we are casting an image first in complex numbers, and also because that is what TensorFlow asks, and that's it. And taking the fast Fourier transform in 2D, and then here I'm just reconstructing it. This is a perfect reconstruction using all frequencies, and here is a reconstruction of the same photo using only 3 frequencies, which is 0.002% of all available frequencies. If we move you can see here using 5 frequencies, and here would be 7 and 15 still. So what we're doing here is just adding, okay? Just adding this more and more of these guys to see what we produce. And it's still not 1%, right? So let's move faster. And this is 1%, 1.1% of all frequencies available. And I think if we move around 2%, it's quite okay. It's a bit 7% is a bit grainy, but it's okay. Still just 7% reconstruction, and you can see this, right? And so now I want to move to my comment on convolution. So you have the kernels. I have several convolution kernels here, but then the pictures are not these guys, but they're Fourier transform. Okay, and so just 3x3 min filter, and Laplacian. You see Laplacian is yeah, it's not this. It's not. This is not this photo. This is the Fourier transform of this matrix here. Then what I do is convolve them, convolve each of those filters kernels, see, and then you get different attributes of changes on your photo. So you can actually see here that the Laplacian is black in the middle and white outside, meaning it kills the frequency near zero, and only the frequency away from zero are alive. So those are higher frequencies. So that is why the photo looks like this. And it's only the higher frequency. And here, the central y-axis is zero, but the other higher frequencies, vertical changes, are not. So you see vertical. Is that obvious? I'm not sure. Vertical lines better. So that is what the kernel does, or in a sense, filter. This is just plotting the Gaussian. So the Gaussian, since what we see here is it slowly kills frequency outside zero, right? So there's only this low frequency existing. So you can see that the photo actually smoothens. Okay, and okay, so before this is the last slide here, the only slide. Just to remind you, SVD decomposed matrix A into orthogonal matrices U and V, and sigma as a singular matrix. Divides into three things, right? You can see it here, SUV, SUV the photo, and then I plot in grayscale the resulting images for the photo for each U and V. For S, there's no point in plotting it. It's mostly zero. So we just look at their values. You can see that the singular values goes down very quickly. So the biggest one is the first one, what is it? And the second biggest one is the number. So my observation here is that to recover the photo, you need to multiply these matrices, right? These are matrices. So this, you can see in the photo, this seems like a low frequency here, and also a low frequency here. So that means that those guys react to the first singular value, and so forth. So the farther you go, the higher the frequency you move, they correspond, their effect, their weight corresponds to the lower singular values. So let's see that claim. So this is reconstructing the photo using the first one, using the first singular value. You can still notice the but the difference between Fourier transform is that seems like it's not so low. The frequency is not so low, and also it's a sum. I think we've done this before, so this you can reconstruct your photo in the same way. And you can skip this. So what's interesting, if you play around, so this is actually the reason why we decided to have this talk, is I was interested when Mrityunjay gave us some visualizations for this, and we play around the singular values. I was interested, how can you control that with idea, like you are in control, you know what will happen, right? So what I'm doing here is that I am multiplying this every, say, the first eigenvalue, I'm multiplying it by 1. Second eigenvalue, I'm multiplying it by 2 squared. The third eigenvalue by 3 squared. So that means I am increasing their factor. So my claim earlier says that each eigenvalue corresponds to frequencies. So the lower eigenvalues we go, the higher frequencies we have, right? So do we really have yeah, here. So this is the reconstruction. It's very high frequency as claimed because we are increasing, we are rescaling the higher eigenvalues by some big number, which is their location squared. And you can see that this has higher frequency if we look at the Fourier transform of this photo, which gives us this. And you can see that there's black on the X and Y axis because this is a high frequency photo, and that there's light and distortion outside. And this is it's not so interesting. So instead of increasing the weight for each singular values per location, I am making it smaller, basically. Retain the first one, the second one multiply by 1/2, third one multiply by 1/3, and so forth. Get something like that. And this is, it's not so surprising that we get that. So okay, I'm really over time, so I think that's all I want to say, really. Thank you.
All right, so thank you, Jason, for the presentation. Does anybody have any questions?
Can I ask a question?
Yes, please.
So what was the intention behind squaring the position of your component and then showing that?
Just, yeah, this, because I claimed here that each of these eigenvalues, so I claim here that the first eigenvalue corresponds to low frequencies, and then the more lower you move corresponds to higher frequencies. And what I did here is to increase the value multiply something, rescale the singular values based on its location. So that means singular values which are around 100 will be multiplied by 100 squared.
I mean, why is that? Why did you choose to, just to enhance the image, right?
Yes, you can do anything, but this is kind of the easiest way for me. I was just lazy.
Theoretical reasoning behind
No,
this.
no. There's no theoretical reasons. I just want to simply write a command.
So that you can see it clearly, right?
To increase the weights of. That's it. And then yes, as we can see here, and it actually only has higher frequencies.
That makes sense. Thanks.
I would like to have a question about when you did the slider thingy for the first slider thingy for the DFT. I think that one, or above
this one.
This one. Yeah. So what is T? What are you here setting?
No. Yes. T is just, it has this
threshold, right?
Yes. Basically just a threshold. So if I'm gonna run you to this thing, what I'm getting here, M, I put M to be the biggest of this
the frequencies.
Yeah. So if we look back here, so among these guys, which is the biggest? I asked, right?
Yes.
Because everything is complex numbers, right? So everything has size, right? So I just say, okay, I want to know the biggest one, and then I'll put the threshold such that I will only use like the top those functions which are, let's say, 1/100 of the biggest one, bigger than that. And then I'm just moving. This is arbitrary. I just wanted it to be This is why it shouldn't be shown. I just wanted this to work and as quickly as possible. Yeah. So yes, that is what I want to do. I just want to put a fraction. So that is my threshold. That's a fraction of your biggest. And as you can see here, I needed really a big fraction because the range are quite different. So that means this could be 1,000,000 and the other ones could just be running around hundreds in terms of magnitude. So that's why I needed this ridiculous 10,000 here. And then this is just to actually get the threshold, and that is just to write the percent accurately there.
And just to remove the noise, if I'm not wrong, right?
Not noise. Basically, so if we look at these photos, everything has a magnitude, right?
Mm-hmm.
Like take this magnitude of
frequency.
Yes.
Frequency has magnitude.
Each of these, because these are complex numbers, right?
Yes.
Each complex numbers you can get the magnitude. That's just yes. So that means you can rearrange these guys. Okay.
Yes.
You can rearrange them in such and you can put like I want to use the.
Oh, so you are ordering it.
Not yes. No, I don't need to reorder it. I just cut them. Imagine if of this grows like a building towards your face now, from the screen to your face, their height, and then you just cut. You just chop. I'm gonna use only this. Yeah, this one's on top, and then you lower your cut.
The frequencies above the threshold are get included, and the frequencies below the threshold
are zero.
Thrown out.
Yes, they're just zero. I just kill the frequencies below the threshold. So that is how I know how many frequencies I have. So here it says I have 3 frequencies using that threshold.
Okay.
Yes, and here I have 9 frequencies. So that is how I know. I just make the other guys 0. 189.
Okay, yeah, now I get it. And so basically the number here, which is I think now 603, that's how much you have out of. It would be interesting to see like how much data points you have in total.
Yes. I mean, we can look at the size of the image. What is the size of my image? It's 376 by 363. So that is the amount of frequencies you have. Because as I've mentioned here, the number of frequencies you will get would be the amount of your
the size,
yeah. So that is how I know this this percentage here, because I'm actually just using the product of the shape of the function, just dividing it by that.
Okay, thanks. Any other questions?
Jason, that's a good presentation. Thanks for that. I mean, I just want to understand one thing. Generally, if you see in either image processing or computer vision, they do operations on spatial domain. They don't go for frequency domain, which is computationally expensive. Do you aware of any case where we have to go for spatial, frequency domain?
As I've mentioned earlier, I just recently moved to application, so I don't know if that's really.
Do you agree with me? It is a computationally expensive. I mean, rather than processing the on the spatial domain, computational domain, I believe it is computationally expensive. I mean, people don't prefer go for frequency domain. I agree. There are some uses where you get the separation of high frequency and low frequency separation can be done easily in the frequency domain.
Yes. Yeah, like computing convolution actually using the kernel is quite easy. So this is just convolution of my photo with this exact with this matrices here, right? So that seems like a very simple calculation rather than playing with frequencies. Yeah, but I wouldn't count that. I'm actually trying some layers that would use
maybe I can add
a frequency domain.
Something interesting here. I didn't follow who was making the comment. Was it Milton J?
No, it's Viru.
One interesting thing about FFT is how I got introduced to FFT and where I was a little bit connected to it and when I used it a little bit, it was for arbitrary large integer multiplication. So it's an interesting fact. So the fastest integer multiplication algorithm, when you're not doing like the small integer calculation, but like huge, like millions and millions of digits long numbers, when you're multiplying those, you have to use, I think it's called a Schönhagestrasse or something like that. So you have various algorithms which are based on a Fourier transform. And the funny thing is that, so the naive approach to do big num multiplication is a n-square algorithm. But if you use FFT, fast Fourier transform, you can get away with n times log n, which is below n squared. And the way you do it is you do an FFT, a fast Fourier transform, and then instead of multiplying every digit with every digit, which would be your naive, like how you do multiplication in school or in kindergarten or whatever, like the paper calculation, instead of that, you do the fast Fourier transform, which is not so expensive. Then you do a digit by digit multiplication, which is linear. And then you have to do the Fourier transform again, which is the inverse, basically. So the inverse Fourier transform. And in the long run, that's a cheaper one. So that's less computationally expensive. So that's just an interesting fact. Does it really answer the question? It's not a clear connection, but like, who knows, maybe in the future, some interesting research.
I agree. I agree, actually. The other thing, what I'm trying to find out here, if you see, the image, if you see before it gets as intensity values, it is a kind of signal that is coming from the camera. So that signal decomposed as digital numbers as intensity values. Then once again, we try to find out some information by applying spatial or frequency domain. So there are some algorithms which are based on the frequency domain, especially if you consider the imaging domain. But I am trying to understand. I was assuming I was thinking if Jason has done some investigation in the frequency domain, is there any way? I have done some experimentation using SVD also, as he has done here.
Yes.
SVD,
I cannot say about about being computationally expensive or not, since personally I don't have much experience. But what I do have confidence is that I can have better control if I am in the Fourier domain, as I am showing. Is my slide still showing?
Mm-hmm.
As I am showing here,
yes.
because this thing here is a simple multiplication. So that means I can really play with this filter here.
Yeah, and just to get back to what I was explaining previously. So on the left-hand side of the equation, you have a convolution, which is computationally expensive, while on the right-hand side, you have a simple multiplication, which is way cheaper. Am I right? Am I correct?
No, I don't think so. The convolution, it is based on the kernel, right? Each time you apply the kernel, and the multiplication, if you see, you have to multiply the whole matrix in a single time. That's where the convolutional neural networks and the fully connected neural networks, if you see the trade-off between fully connected and this one, convolution is better. It is because it sees, at a time it gets multiplied with a patch of data, not the complete data. So I think,
in terms of really computational cost, I cannot say anything. But in terms of control, we would have better control.
This is again, one more thing is I'm thinking this is a spatial domain, right? If you take one image, if you try to find out the high frequencies and low frequencies, separate out high frequencies and low frequencies. I mean, SVD is SVD still is a computationally heavy. I mean, if you want to decompose assume 1000 by 1000 1000 by 1000 image, applying SVD it takes lots of time. So and I mean, as it is a single signal image, if I consider image as a single signal, applying FFT and getting some information out of that is, I'm just thinking, how does it make sense when you have an audio signal? Assume audio signal is a kind of sequence of signals that you have. You can dunk. I mean, FFT is largely used in audio signals.
Yes,
so
absolutely.
Those are I mean, small signals, and you can find out the peaks in audio tone, and that is highly, I mean, highly stressed FFT in audio. But image, I am just trying to find out, is there any case that we need to go for FFT rather than spatial domain? So yeah.
I'm sorry, I cannot answer about
fine.
The cost. Yeah, but just to add, we should not this multiplication here. We should not belittle this simple thing, because actually some results in physics that I've done is because we have shown that it's a solution of a Schrödinger equation is simply existing in the Fourier transform space on the parabola. Like, how would a parabola be in quantum mechanics? Like, things like that are seen and by this simple multiplication aspect, and because things happen with when you want to go back. So, in terms of control and definitely innovation, if you think in terms of frequency.
One more thing is, when you showed the SVD demo, right?
Yes.
So SVD demo, as far as you know, if you see the eigenvalues, I mean the eigenvalues decomposition, eigenvalues from the beginning, they represent high frequencies. The high frequencies is a prominent region in image. The more that you go down, they represent the low frequency. So that's where image compression. It's not the case.
Sorry, yes, that was actually my realization while playing this. The first one corresponds to the lower ones, to the lower frequencies, and the more you go down, the higher they become. So that is the reason we got this photo here, because I am increasing I am multiplying something on for the lower ones, while the first one remained as it is, because for the first one I equals 1, so it's just 1, but for the second one I equals 2, so I multiply 2 on the second one, then I multiply like 100 on the 100th one, so they become bigger and bigger. What we can see here in the reconstruction is that it seems like a high pass filter has been done. And to verify my claim, and actually you can see in the Fourier view of this photo that indeed the frequencies at the center, the ones near zeros, or the simple ones, are shut down. They're zeros. They're black. So the frequencies, they are higher frequencies. The lower you go here, the more you go to the right, the higher frequencies we get.
So here x-axis represents the frequency, I mean, number of frequency, number of
this is the actual matrix, actually. So yeah,
in a middle diagram that you plotted.
This one. This 0 is the first or 1 is the first eigenvalue, and then as you move that, so that's why it shows these values, the singular values, goes near 0 quite quickly, right? It shows here because these are the values of S in this in SVD.
Okay. No, ma'am, I have not drawn like this. I just analyze the singular values. I mean, it's a diagonal matrix, right? Singular value.
Yes, yes,
you
yes.
get
So
it
these
is a
are the
diagonal
numbers
matrix.
of the diagonals.
Yeah.
Yes.
Mm-hmm. Okay. Yeah. I mean, anyway, my understanding might be ulta actually. I did not draw like this, but when I analyzed the diagonal matrix, down, I mean, bottom of the matrix is kind of lower values. So that's how this image compression also people use SVD to compress the image actually. So they suppress the low frequencies so that you cannot visualize the difference between the original one and compressed one.
I'm afraid we're out of time.
Yeah.
I also wanted to suggest we're at half mark point. So I guess I would like to thank Jason again.
Yeah.
Thank you so much.
If we have time, we might get to continue.
Oh, thank you for this opportunity. It's nice.
Great
Yeah.
presentation. Thank you.